Hello friends, today in this video I am going to talk about rotational spectra, silent feature, classification of molecules, rigid rotator, explanation of rotational spectra, interaction of radiation with rotating molecules, intensity of spectral lines, isotope effect, non-rigid rotator and applications. Now rotation of molecules. You know, the spectroscopy in the microwave region is concerned with the study of rotating molecules. Rotation of 3D body may be quite complex. Rotational component about the three mutually perpendicular direction through the center of gravity, the principal axis of rotation, the three principal moment of inertia IA, IB and IC designed. Now, classification of molecules. My friend, linear molecules, atoms are arranged in a straight line like SCL or OCS. The three directions of rotations may be taken as: first one, about the bond axis; a second, end over end rotation in the plane of the paper; and third, end over end rotation at the right angle to the plane. Here IA is equal to 0, IB is equal to IC. Now, symmetric top molecules. Consider a molecule such as methyl fluoride. Three hydrogen atoms are bonded tetrahedrally to the carbon. The moment of inertia about the CA bond axis is now not negligible. However, because it involves the rotation of three comparatively massive hydrogen atoms of this axis, so symmetric top means AB is equal to IB is equal to IC is not equal to IA, I is not equal to 0. So the example of symmetric top molecules is methyl fluoride. Now, two subdivision of this class: methyl fluoride above IB equal to IC greater than IA, then the molecule is called correlate symmetric top, and if IB is equal to IC less than IA, it is referred to as an oblate. An example of layer type is boron trifluoride, which as shown is planar and symmetry. You can see IA is equal to IB is equal to IC. Now, a spherical top. When a molecule has all three moment of inertia identical, it is called a spherical top, like methane. IB is equal to IC is equal to IA. Now, a symmetric top. These molecules to which the majority of substance belong, all are three moment of inertia different. You can see the water, you can see the ethylene chloride. So simple example of water. Now, rotation spectra molecular requirement. Spectroscopy in the microwave region is concerned with the study of rotating molecules. Only molecules that have permanent dipole moment can absorb or emit electromagnetic radiation in such transition. In the rotation of SCL, fluctuations seen to be exactly similar to the fluctuating electric field of radiation. Thus, interaction can occur, energy can be absorbed or emitted, and the rotations give rise to a spectrum. Now, which type of molecule doesn't show rotational spectra and why? In homonuclear molecules like N2 and O2, no change occurs in the dipole moment during the rotation. Linear diatomic molecules are rotationally inactive for rotations about the bond axis. The moment of inertia is very small, 0 about the bond axis. No change in dipole occurs when it is rotating about the bond axis. Homonuclear molecules, however, show rotational Raman spectra, which arises due to polarizability of the molecules. Now, technique and instruments. The basic requirement for the observing pure rotational spectra is observing a source of continuous radiation in the paper, proper infrared vision, a dispersive device and detectors. Now, radiation from the source is taken, which passes the SCL vapor. The transmitted beam falls on a condensing mirror. The collimated beam passes through a rock salt prism. It is poured to a focus at the thermal detector by means of a focusing mirror. You can see the schematic diagram. Source and monochromator. Klystron valve is monochromatic source emit radiation over only a very narrow frequency range. Beam direction achieving by use of waveguide rectangular inside the rotations is confined. Now simple and simple space and fourth one detector. Now molecule as a rigid rotator diatomic molecule. The simple model of rotating molecule is that of rigid rotator. By definition of center mass we have m1 r1 m2 r2 r1 plus r2 is equal to r. From these two equations we have r1 is equal to m2 divided by m1 plus m2 r, and r1 is equal to m1 plus m2 r. Now the moment of inertia of molecule about the axis rotation is given. I is equal to m1 r1 k square m2 r2 k square is equal to m1 m2 divided by m1 plus m2 r square. But m1 m2 divided by m1 plus m2 is the reduced mass mu of molecule, then I is equal to mu r square. Thus the diatomic molecule is equivalent to the single point mass mu at a fixed distance r from the axis of rotation. Such as a system is called rigid rotator. I is equal to mu r. Now surrounding for rigid rotator, which is psi square del square psi plus 8 pi square mu by h square is psi is equal to 0. The potential energy term V has been taken 0 because r is fixed. So in a spherical polar coordinate system, 1 by sin theta dou theta sin theta psi by dou psi plus 1 by r square sin square theta dou square psi by dou phi square plus 8 pi square mu by h square is psi is equal to 0. Using separable variable method, psi theta phi is equal to theta theta phi phi. On solving the separable variable method, we have two equations. d square phi by d phi square is equal to minus m square phi, and 1 by sin theta d by theta sin theta d theta by d theta phi square i.e. h square m square sin square theta theta is equal to 0. The solution of the phi equation is equal to phi 1 by root 2 pi exponential I m phi. On solving Q equation, you have this equation. So the equation is identical to the associated Lagrange differential equation. Provide 8 pi square I h square is equal to j plus 1. So Ej is equal to h square pi square j plus 1. In this expression, h is Planck constant, I is moment of inertia, either Ib or Ic. Since both are equal, the quantity j will take integral value from 0 upward is called rotational quantum number. Now spectrum of rigid rotator. In the rotation regions, spectra are usually discussed in terms of ref number. Epsilon is equal to Ej Sc is equal to h at 8 pi square Ic j plus 1 centimeter. J is equal to 0, 1, 2, 3. So where c is velocity of light, is their expression in the centimeter per second. Epsilon is equal to bj plus 1 centimeter. Where b is the rotational constant is given by b is equal to h 8 pi square Ic per centimeter. From allowed energy transition, you can see. So for j is equal to 0, epsilon is 0 molecule is not rotating. For j is equal to 1, rotation energy is epsilon 1 2b, and rotating molecules at its lowest angular momentum. Now for increasing j value, Ej may have no limit to the rotational energy. So computational force. If you imagine the molecule to be in the ground state in which no rotation occurs, the raise the molecules to j is equal to 1 state, energy absorbed will be epsilon j 31 minus epsilon 30 is equal to 2b minus 0, 2b in centimeter involved. So j is equal to 1 to j is equal to 0 to 1 2b centimeter. Further, if j is equal to 2 to j is equal to 1 to 2, so 4b centimeter. So in general, This stepwise rising of the rotation energy result in an absorption spectrum consisting of line 2B, 4B, 6B per centimeter. We need only consider transition in which J changes by 1 unit. All other transitions being spectroscopically forbidden, such a result, it is called selection rule. So selection rule is del J plus minus 1. Now quantization of rotational energy. Energy and angular momentum of rotor is equal to half I omega square. P is equal to I omega. The energy level expression to EI is equal to J plus 1 H square minus 4 pi square, and P is equal to J plus 1. Now intensity of spectral line. You know, my friend, for the transition state, the energy del J is equal to plus 1, which are forbidden. The transition probability is 0, and the probability of all changes with del J is equal to plus minus 1 is almost the same. This doesn't mean that all spectral line will be equally intense. In normal gas sample, there will be difference in number of molecules in each level. Therefore, different total number of molecules will carry out transition between the various levels. Since the intrinsic probability are identical, the line intensity will be directly proportional to the initial number of molecules in each level. So, first factor governing the population of the level is the Boltzmann distribution. You know, this Nj divided by naught is equal to exponential Eg by kT. So the second governing population of the level is the possibility of degeneracy in the energy states. Now each level J is equal to 2J plus 1 degenerate. Population is greater for higher J state. So relative population at energy Ej directly for 2J plus 1 exponential minus J by kT. Effect of isotopic distribution. You can see the example CO. J is equal to 6, 5, 4 and energy level. From carbon 12, oxygen 6, carbon 13, oxygen 6, mass increases, B decreases. Directly position 1 by A, so energy level lower. Comparison of rotational energy level of carbon monoxide and 13 carbon monoxide. The isotopic mass occurs within 0.02% of the other method for a gaseous molecule. Isotopic distances, abundances from the absorption's relative intensity is like this. Now, non-rigid rotator. In practice, spectrum lines are not exactly equidistant. Separations decreases with increasing J. So molecules stretch and become non-rigid with increasing rotation. The correlation term of, containing the centrifugal distortion constant D, which correct for the fact that the bond is non-rigid. Now spectrum of non-rigid rotator. The Schrodinger equation is set for the non-rigid rotator is like that, and where D is centrifugal distortion constant given by. So application of microwave spectroscopy. Chemical analysis by microwave spectroscopy. The rotational spectra of a substance at room temperature can examine accurately. Molecular identification in phase. Electronic spectroscopy has been able to detect the presence of various atoms, ions and few radicals in the light of the star. Recently, simple stable molecules in space detected by using microwave spectrum. 130 molecules and have been identical in interesting space by their rotational emission spectra or RF astronomy. Now microwave oven. Do you know what is the basic principle of cooking in the microwave oven? Its mode of operation depends entirely upon the absorption by the food of microwave radiation.